Well, I have managed to show the part A calculation briefly here on your screen. Data is also listed here. We can proceed for parts B and C on this page only. Having a look at the question once again, in part B, find the average and maximum powers of the engine. So we shall do it now in part B. Since the work input by the engine is this, W dash, and the interval of time, delta t, in which this work has to be done is also given, we can write down the average power supplied by the hydraulic press, that is work input divided by the interval of time in which the work is done. This is 2.32 into 10 to the power 5 joule divided by delta t is 45.0 second. Calculation shows this is coming out to be 5.16 into 10 to the power 3 watt. Capital W is the symbol of watt, the SI unit of power. Don't confuse it with the symbol capital W used earlier to express work by the press. So that we can express to be 5.16 kilowatt, kilo being the prefix for a factor of 10 to the power 3. Now what about the maximum power supplied by this engine? Well, we know that power is scalar quantity given by the dot product of two vectors, force and velocity vectors. Here force is the one applied by the piston and V is the velocity of the piston or this compressed load. Since F and V have the same direction, that is vertically upwards, we can express power to be the product of the magnitudes of force applied and the velocity of the piston, and assuming that the piston goes upwards slowly with a constant speed. In such case, V remains constant, and you can write down the power supplied by the engine is directly proportional to the force applied by the piston onto the load. This is true for V constant, which is the usual case assuming the piston is advancing upwards at a constant speed. So we can write down that the ratio of average power and maximum power supplied by the engine is equal to average force applied by the piston divided by the maximum force applied by the piston. From this we could write down the maximum power supplied by the engine equal to average power supplied multiplied by maximum force applied by average force applied. Well, look here, F max, that was explained to be mg plus F2, and average force that was found to be mg plus F2 by 2. So I put those values to write down P max is equal to P average into mg plus F2 divided by mg plus F2 by 2. Remember, we can write all these things with the condition that the vertical strain on the load is directly proportional to the compressive force applied. So once we get this, let us put the values next. We have maximum power supplied by the engine is equal to average value of power that was found here, already calculated, 5.16 kilowatt, multiplied by, in the numerator we have got M. Well, the data is waiting for us here, 3.75 into 10 to the power 4 kg into G, that is 9.80 meter per second square. This plus F2 5.00 into 10 to the power 5 Newton. That was numerator. Come to denominator, this is 3.75 into 10 to the power 4 kg into 9.80 meter per second square plus F2 by 2, which is 5.00 into 10 to the power 5 Newton, this quantity divided by 2. Just a little bit of laborious calculation, nothing else, and show that Pmax I am getting to be 7.25 kilowatt in 3 significant figures. Just confirm this. This is the answer of second part within part B. So let's look at once again. We have got the average power supplied by the engine is 5.16 kilowatt. So the maximum power delivered by the engine, which corresponds to the maximum strain of the load, that is 7.25 kilowatt. One more part left, and as before, we shall just show here only the main steps of calculation to avail some space for writing. So ready for part C of the question, and having a look at question once again, you find the number of strokes of the smaller piston if it is lowered by 10 centimeters per stroke. So we already noted down earlier symbolically delta H1, that is distance travelled downwards by smaller piston per stroke. This is 0.100 meter per stroke. And let me assume that n such strokes of smaller piston is required to compress this load accordingly. So if per stroke the displacement of smaller piston is delta H1, after n such strokes the total displacement of smaller piston will be delta capital H1, that is number of strokes n, into the distance travelled per stroke, is not it? N into delta H1. Now the corresponding displacement of volume of liquid, the volume that is displaced in the smaller cylinder, that is left one cylinder, not shown in my figure here, that volume of hydraulic oil displaced will be V1 equal to delta H1, the distance travelled by smaller piston, multiplied by its cross-sectional area, which I take to be A1. So this is coming out to be N into delta small h1 into A1. Now come to the right side piston in this wider cylinder. The volume of hydraulic oil displaced V2 is equal to delta H2, that is final displacement of this piston in the upward direction, multiplied by cross-sectional area of this piston that was taken to be A2 earlier in my writing. So since this hydraulic oil is an incompressible liquid, we may assume that this V1 and V2 will be the same. V1 is the liquid that goes downwards under the smaller piston, and V2 is the volume of liquid that is going upwards by the push of the larger piston. Now if V1 is equal to V2, we can write down that since V1 equal to V2, it follows that N into delta small h1 into A1 equal to delta capital H2 into A2. We are looking for small n here. This is coming out to be delta H2 into A2 divided by delta small h1 into A1. Let us put the values. Delta H2, that was given to be 0.300 meter. So I write it here, and in denominator delta small h1, that is 0.100 meter, and the ratio A2 by A1. It was listed earlier that A1 by A2 is 1 upon 60. Therefore, A2 by A1 will be 60 in the numerator. Go for the calculation and show this is coming out to be, well, let me write separately here. I am getting n is equal to 180. And that is the answer of part C of the question. I'll tell once again, we have got in part C that 180 strokes of the smaller piston is required in the downward direction to make sure larger piston goes upwards through a distance of 30 centimeters, and that is the maximum compression of the load under question. Here is the end of this problem.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.